Hello, everybody coming in. Oh, there we go.
Hello.
Hello, everyone. Welcome, welcome, welcome to, and Happy New Year to the new year. And we welcome you to the first AI meetup of the year. My name is Vanier. I am the Marketing and Communications Associate at Amii. Please take a moment to unmute your microphone and introduce yourself. Tell us what you're working on and which part of the world you reside in.
Randy Goebel, University of Alberta, AI professor and a number of other odd jobs.
Nice. Welcome, Randy. Nice to have you. So thank you all for bearing with us as we're letting people in. Please, for those that are just coming in, please introduce yourselves. Let us know where you're from and what you're working on.
I'm Ian Verhappen. I'm with Willow Glen Systems, solution architect, and we're working on a next generation SCADA system that hopes to incorporate ML.
Excellent. Nice to have you.
And I'm here in Alberta as well. Our headquarters is Edmonton and I'm in Calgary.
Excellent.
My name is Thomas Stoker. I live in Calgary, but I work for Wonder AI, which is a startup located in Toronto, Ontario. I work as a chief data scientist, and what we are working on is we are developing artificial intelligence that could provide automatic art appraisal. And that's about it.
Excellent, Thomas. Nice to have you.
Thank you.
My name's Steve Pearson, and I work for a startup called Vino AI, and we're using machine learning in our recommendation engines to provide personalized wine recommendations.
Excellent. Welcome. Nice to have you. So it looks like we are just letting the last few folks in. So I'd like to say again, welcome back and Happy New Year to you all. My name is Vanier Rak, and I am the Marketing and Communications Associate here at Amii. For those of you who are recurring AI Meetup attendees, our regular host Warren is unable to attend the meetup this evening. So I will be helping guide the meetup along this evening. And for those of you who are joining us for the first time and haven't heard about Amii, Amii is the Alberta Machine Intelligence Institute. We are one of 3 centers of excellence as part of the Pan-Canadian AI strategy, with a history reaching back to decades of world-leading AI research and training that has put us in a position as one of the global leaders of AI and ML. So whether you're a business or you're a student or you're just looking to get involved in the AI community, Amii has a whole host of programs and resources to support you, and we'd love to connect. So please reach out to us via our website, amii.ca, or send us an email at hello@amii.ca to learn more. But a few housekeeping notes before we get started. We are trying to keep this relatively brief so you can get the most out of your evening. So we can all expect this meetup to be around 1.5 hours. The meetup is being recorded. So in case you aren't able to stay with us the whole time or are frantically taking notes, don't worry. We will have this meetup up on our YouTube page as soon as possible so everyone can view it at their leisure. But regardless, we are excited to see all of your faces and encourage you, if you are comfortable, to keep your camera on throughout the meetup so our presenters can see you and gauge your reactions. And finally, as we continue to improve these virtual events with each iteration, you can expect an email after this meetup with an incredibly short survey to let us know how we did and what we can do even better. So do take your time. Please give us the feedback. A minute out of your day will help us immensely, and we will be grateful. But housekeeping aside, we have 2 great presentations for you this evening. There will be a quick 5 to 10 minute Q&A at the end of each presentation for any questions that you may have for our presenters. at which point you can send your questions into the chat, or you can freely unmute your microphone during the Q&A period to ask your question verbally. But without further ado, you are here for the content. So please let me welcome our first presenter, Chris from ISAIC. Welcome, Chris.
Thanks, Vanier, and thanks very much for having us today. I'll just pull up my screen here so that hopefully you can see the presentation. Is that clear?
Yep, looking great.
Right on. So just as we get started, I'm Chris Vanier from ISAIC, also located at the, or like some of the folks here, located at the University of Alberta in the Faculty of Engineering physically, but obviously working virtually like many of us or all of us right now. With me here today is Francois Brochu, our Senior Systems Administrator, who will also be speaking, and a note out to Dr. Edmund Lau, who is our Principal Investigator and was part of the founding group for ISAIC when it was initially started back in 2017. We're also really happy to see Randy and other familiar faces and supporters who are helping us get to the place in the ecosystem that is good for everyone. So today's presentation is somewhat informational and educational, or that's the intent. And as we get started, we'll just be talking about hardware that powers the AI process, and then specifics around GPUs and more technical components, as Francois will discuss that, and then a little bit more about ISAIC at the end. Just a shout out with the poll, it'll pop up in just a second. If you want to share with us who is coming in from the research community, from the business community, or if you're just here for curiosity, and how familiar are you with different computing resources for AI? The lovely thing about an active poll is that we all get to see the results. So Vanier, do you want to?
Yeah, the poll is live.
Yeah. So it's great. We've got a good mix of everybody. So we definitely welcome throughout the presentation that you fire questions into chat, and also save verbal questions for the end of the presentation when when the forums opened up. So I'll just go to the next slide. And really the reason that we're here is ISAIC is looking at the applied applications for AI, and the 53% of companies that are currently not using AI, and the 33% above that who are looking to start some AI initiative in the next year. So obviously we all have this tremendous amount of interest, and that's why we're here supporting Amii. And, oh, my slides are skipping around here. Maybe close the poll. So that's where ISAIC fits in, sorry for that. That's where ISAIC fits in. It's really the hardware and the infrastructure support and the tools and the equipment that enable local businesses to adopt AI. And as we get started, we'll talk a little bit more about hardware that enables that process. And to put that into context, we really look at three major foundations to AI: compute resources and the tools, the data, and then the people and human competencies that are really critical to actually adopting and getting through the commercial journey or a research journey for any AI project. And the reason that we exist is for that compute item that really needs to be considered in the project charter and early on in the design phase. And what we've learned from our clients often isn't necessarily considered up front. There seems to be a lot of resources available, and we have the opportunity to speak with a number of clients and try to support their different challenges and make sure that computational resources are well understood in their enablement of your AI and machine learning projects. Some of the things that have really been key for us is making sure that folks understand the cost and the line item right at the beginning so that they're not subject to data or egress fees later on. Another thing is the fast evolution of compute and the time it takes for maintenance, upgrades, and the realities of depreciation, again, as a line item when things change for this whole industry so quickly. And now I'll turn it right over to Francois to get into the meat of the presentation.
Okay, exploiting the GPU. In the next slide, we're going to see why elastic computing is important. Elastic computing is because you need whenever you're going to be using machine learning or deep learning or whichever learning that you're going to be teaching the machine, it's going to change because you have data collection or your data selection, you have your pre-processing. So is those images, are they images, are they black and white, are they color, are they text with non-applicable field, any field and all that. So you're going to be doing pre-processing, you're going to be transforming your data, and then you're going to be doing model building. Each one of those steps has different need for processing. Some of it you could do on your laptop, but eventually you're going to be needing a lot of GPU when you're sorting your images. That's a RGB and it's a high definition images. You're going to be needing a lot of GPU power and the TensorFlow powers. On the next slide, we have dedicated hardware. So why is that important? Your AI application, whatever your application is, will rely on the hardware as a core enabler for debugging. I'm not feeling comfortable to send my job, to write a job and send it in the queue and wait 2 weeks to find out that I missed a semicolon somewhere. And now I have to go and rewrite and put it back in the queue and wait another 2 weeks. I want things to work right now. I want to find out and fix it right away. And that's the reason that we have dedicated computing. It's why wait in the queue for success? With dedicated computing and general purpose, there's no schedulers and there's no over provisioning. So when you have the GPU or you have the CPU, you got 100% of it. Often enough, you'll have a company where they over provision the CPU because you can, and you could over provision the memory, and they make you believe that they have like 100 times the size that they really have. And then you have to wait in queue or share with somebody else the CPU and that kind of stuff like that. With us, it's just like that the VM is sitting on your desk, is 100% dedicated. Next slide is we're talking about elasticity and flexibility. Very important is when we're talking about data that it is an image or it is a sales ribbon or some event that happened. We collect the data, like I said, you could or you're taking some picture that could run from your cell phone, a Raspberry Pi, an Internet of Things, or even a laptop. But once you really need to clean it up and pre-process it, you're going to need more. So you probably could use a GPU, or you may not need. You could need more CPU. And as you move it along, you will actually need more powers. And then it's going to go back down once your model is developed and your model is fully trained. And you could be back to your cell phone taking a picture, and it's going to tell you, oh, it's a cat or it's a dog. Typical machine that we have all the time that shows up. And this is where we're going to be needing some the difference between the computing force and the how does it scale. When there's CPU, GPU, TPU, NPU, DPU, PU, that's pretty stinky job here. But the difference are between a CPU and a GPU is it's how it does. All these all they understand is zeros and one. So how does it scale? Is it an array, a single array, a multiple dimension array, or is it a tensor with a multi-dimension of array to do multiplication? It just runs faster. It runs 1,000 times faster on a tensor processor. And that's why you want to be using. And NPU, so CPU is the computer processing unit. The GPU is the graphical processing unit that handle good to 2 to 3 dimension array. And the TPU goes much more than that. NPU is fairly new. Not everybody I've heard about that. It's for the neural network processing. So it allowed the neural processing unit. And the DPU is for data processing unit. This is the latest from NVIDIA. Well, I don't know about the latest. And how does it compare? How does our hardware compare to Compute Canada, Cyberra, Google? Most of them, when you go there, unless you're paying premium, you have the older hardware. So if you're comparing a P100 to a V100, this is what we have. On a DL training, we're looking at about 12 times the performance. DL as a deep learning. Inferencing is 6 times faster, and so on. Once again, because we have dedicated hardware, not over provision and no schedule, our hardware is ready when you are. ISAIC Garage. So what's an AI Garage? AI Garage is everything that you need is there. Well, most of everything you need. So we still have the you still have the opportunity to install whatever that is a newer library. So in our current infrastructure, we have a stack of hardware, and we also have an environment that features some high-end workstation. Remember these, the stack runs in the cloud. So we have, this is going to be for people who likes numbers and they want to compute a lot. We have 20 computing nodes, 824 CPU cores, and each node has a terabyte of RAM. We have 136 GPU with a 16 gig of memory. Per GPU with a single precision is 17 teraflops. And we have a 5,120 CUDA cores and 640 Tensor at 125 mixed precision. A teraflop is a trillion floating point calculation every second. For those who've been following like CFAR 10 or CFAR 100, those models were developed on with 600 megaflops. So we're looking at something like 1 million times bigger and faster than when CFAR 10 and CFAR 100 was open. Our typical offering is you could get a VM with a CPU or a single GPU, 2 GPU, 4 or 8. Those are, at 8 GPU, it's easily managed by CUDA and NVIDIA. Anything over 8 GPU, like if you want to have 12, 24, or 48 GPU, we need to build custom because we don't know if you're going to be using Spark or are you going to be using MPI, or do we need to set up NFS for you, that kind of stuff like that. We have a network that's actually quite good. We don't use we use 4 10 gigabyte redundant network for communication. So it's it's pretty fast. And with that, we could actually build anything special for you. Next slide. It does get complicated. So if you need to maintain, like Chris mentioned earlier, computing has to be a line item. So is it a line item or is it a project to manage your hardware? Because with CPU, GPU, TPU, and PU, and then you have how those GPU are connected to your hardware. Are they using PCIe Gen 3, PCIe Gen 4, PCIe Gen 5? And what does those PCIe mean? Well, for example, PCIe Gen 3, it's what's typical on the computer, everybody's computer. PCIe Gen 4, it's twice the speed of the Gen 3. And Gen 5 is going to be twice the speed of Gen 4. And then you have to keep up with the NVDL driver. So you get a security update that Ubuntu just pushed. Your NVDL driver doesn't work anymore. It needs to be rebuilt. And your Tensor, because you have rebuilt your NVDL driver, your TensorFlow probably going to need to be reinstalled. So it does get complicated. So with us, it's much more simple. You turn on your machine and it should be working without problems. Next slide. Well, AI solution to the next level with NVDL V100 Tensor is ideal for deep learning, machine learning, reinforced learning, sure. Graphic processing, text processing, it's all good. It's all easy. It's CUDA, pretty standard. So you don't have to, there's a library that exists all over the place. And at GTC library, there's tons of oh, it's escaped me again. Sorry about that. There's a ton of application already that you could actually use a Docker to actually download your Docker inside and just run with it. So you don't even have to develop your model. You could just use it that's already optimized. On this, I'm going to pass it back to Chris.
Thanks, Francois. So just to talk a little bit about ISAIC's position and maybe provide some context at a higher level in Canada. So we're happy to be working with Amii and a number of partners, and many of you may know these organizations. If you're involved with the research community, Compute Canada provides, or soon to be NDRIO, provides the environment for many supercomputing applications across the country. And there are commercial cloud providers operating in Canada. And why this matters is really about the positioning. So for large multinational infrastructure providers, there's a number of unknown or relatively unknown costs and risks that we also more locally look to mitigate working with companies. So a big difference that many folks don't know about when they're first starting, or maybe traditional businesses are already having this experience with their current provider, is the egress costs. So most organizations have programs for credits or supplements when you bring your data in. And I think that most of us have heard the expression data as the new gold or data as the new oil. And that's really exciting for all of our futures and the future of all of our businesses here locally. Yet on the other end, in a brilliant business model, they also charge fees to leave the environment. And this creates a stuck cost that we really want to share with businesses and help businesses locally understand that we're looking to provide a really strong compute environment and enable the local ecosystem without the risk and with an affordability that startups and SMEs can adopt AI. The other major consideration most folks ask us about is security. And at ISAIC, we really look to the HECFAT, which is an educational institute security protocol. And it maps really closely with many of the known protocols in the broader community. So security is something really important to us as well. And when you're considering your projects, that's a likewise consideration. So we're really happy to be able to offer an environment that can meet all of these standards. A sense of our clients. So we do focus on startups and SMEs in the community, and we also work with researchers, particularly instructors who are looking to train folks in AI. We're happy to work with partners like Amii and Cybera, who offer different courses and look to train folks in AI. So the benefit of, I guess it didn't flip to the next slide here. There we go. The benefit of having all of these different client types is that we can really facilitate coalitions and the matchmaking that really drives innovation and drives new solutions within a secure data environment. Some examples of our clients are here folks maybe you know locally, and that that the type of activities we undertake are really technically focused. Case competitions for applied AI solutions on behalf of business. We just did the hackathon last weekend with the Faculty of Engineering, Connectathon, and coffee sessions. So those are the type of things you would see from ISAIC, as well as us in community working with Amii and their events or any other ecosystem supporter. A big goal for our business also is the Sandbox and where we're headed. And the goal, bringing together all these different client types also gives us that sandboxing and safe sandboxing environment to allow you to tackle your AI projects, or just in general, that compute becomes a foundation, that it can be something that's worry-free, so that there's the space for innovation and for the AI interested or passionate professionals, that they can come to a place where there's other like-minded folks and work together to solve problems. So that's where we're positioned. And I hope, although we covered a lot of information today, some of it was highly technical and some of it high level, that there's really a couple major outcomes that we really do want compute to be simple for business. And it does make it is part of the considerations when undertaking an AI project, and that we're here working from the University of Alberta in order to support your work or your interest in AI. So with that, I can open it back up to Vanier for questions and invite anyone to reach out, even to our tech team through the chat.
That's great. Yes. Thank you, Chris and Francois. Yes, please take a moment to ask your questions. Either unmute your microphone and ask your question, or feel free to pop your question down into the chat. No questions for ISAIC?
Be quiet.
Everyone wants to learn about explainable AI.
I don't have necessarily a question, but on behalf of Amii, we are very excited to have ISAIC as a partner. And we've also have co-sponsored the HackEd hackathon as well, which was, I think, a very, 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 very great annual venture. Ian asks, will you be sharing the survey results? Certainly, we can certainly do that. Okay, well, if there aren't any questions, we can feel free to move along. At the halfway point of the meetup, we'd like to take time to allow everyone to give a brief shameless plug about what they're working on, if there's any exciting news happening on behalf of yourself or your organization, whether you are looking to hire or you are looking to be hired, or if you're just looking for mentorship. This is a great chance to raise that awareness of what you are looking for within the community and what you're looking forward to. So does anybody have anything exciting to share at this time? And it's okay if you don't. These meetups are always either very talkative or not very talkative, or somewhere in between. So okay, very well. Let's move on. Actually, no. Before we continue, we have some news on Amy's behalf. The AI for Good Lab the AI for Good Lab applications are now open, is what I'm trying to say. The AI for Good Lab brings together a cohort of women who study at the undergraduate level or have graduated within the last 2 years and have prior experience with coding or advanced math, such as calculus, linear algebra, stats. The program offers a robust intro to AI, and there are actually 2 independent programs happening concurrently this year. There's a program happening in Montreal and a new pilot program happening here in Edmonton, which will be hosted by Amii. I'll plug the URL into the chat in case you or someone you know might be interested in applying. But while I do that, I'd like to introduce our second speaker, Brittany Davis, who is a Master of Science student at Washington State University and a graduate student within the Intelligent Robot Learning Laboratory, directed by Amii's fellow in residence and associate professor at the University of Alberta, Matt Taylor. So please join me in welcoming to the virtual stage, Brittany. Thanks for joining us.
Hello, good evening, everybody. My name is Brittany. I go by Britt. I am extremely honored to be part of Matt Taylor's interactive robot learning laboratory. It's a great opportunity for me because I'm not actually in Alberta. I'm in Washington State in the United States. So I am currently on leave from Pacific Northwest National Laboratory, and I'm finishing my master's thesis at Washington State University in computer science. What my thesis is about is visualizing reinforcement learning. You're probably all aware that machine learning can be a little complicated sometimes. And with reinforcement learning, that's a little bit more true because you have the extra dimension of time. So what is reinforcement learning? Well, at its most basic, reinforcement learning is the diagram you see on the right hand here. Basically, the AI can be thought of as the agent, and the agent exists in some environment. The agent has a set of actions it can take, and every time it takes an action, it gets feedback of some kind from the environment. You can think of this as maybe a self-driving car simulation that hits the gas when it sees a car stopped in front of it and causes an accident and gets feedback that the accident is bad. You can also think of this as maybe putting like a very small child into a carrier with a bunch of new toys hanging over its head. And the child is very young and doesn't really know how the heck its limbs work. So it's got to figure that out first. And then once it does that, it has to figure out how the toys hanging above it work. And then once it figures those 2 things out, it can maybe interact with the toys in like a way that gets them somewhere. That is to say that a reinforcement learning agent needs a lot of training. And that means that we don't have to like handcraft features or interactions in the environment, but we do have to wait a really long time for the agent to figure it out. So that's the pros and cons. I have had some people just tell me like, this means that reinforcement learning is not going to work. It just doesn't work. Stop working on it. It's ridiculous. Could be true. I don't think it is. Because if you think about one of the types of machine learning that most people are familiar with, like an image classifier, you train the image classifier. And once it's trained, you give the image classifier a bunch of images. It gives the images labels and then it's done. But if you think about all the robots that you see in Hollywood movies, they don't just wait for one particular task to come along, do the task, and then like shut down. They interact with the world in an ongoing way. And so if we kind of want to get to that point where we have AI that does that, I really think that reinforcement learning is going to be what we have to focus on and what we have to work with. Unfortunately, like everything else in machine learning, the state of the art in reinforcement learning is deep learning. And deep neural networks can be complicated, complex. What we have here on the right is actually a diagram of the type of algorithm, the type of network used by the algorithm that I used in my thesis. It's called DQN. And you can see there's like the 3 dots at the end of the layers. That just means there's more layers, which means it's big. There's a lot of nodes, there's a lot of layers. And what those layers can do is they can approximate a function, but they can also make it very difficult to untangle why an agent is making the decision that it is, because its decision is made because of that function. If you want someone to get into a self-driving car every day and take it to work, they're going to want to know things like, why did the car decide to get into left-hand lane there? Or why did the car slow down there? Why did it take a right turn there? If you have to give them the answer of, I don't know, they are not going to take that car to work. So we kind of need to figure that out. Reinforcement learning in particular basically right now uses these two techniques to do visual explanations. On the left-hand side, you see the rewards over time graph is what I call it. And basically it has a line that shows you how the agent's rewards are changing over time, either during training or during some evaluation. The problem with this is that there's a couple different problems, but one of the main ones is that you can't really see something like if the agent finds something that gives it rewards, but doesn't necessarily take it towards the goal you're trying to get it to do. If it just sits there and does that, it can sit there and perform this reward hacking operation over and over again, look like it's doing really good in your chart and not be getting where you want it to get. Not good. Because of this kind of thing, people started doing the right-hand side, which is something called saliency maps. And in a saliency map, the part that's brighter in the image indicates a part that is more highly activated in the neural network for the input. What this is supposed to show us is the places where the neural network is looking in the image. That might not be true, it turns out. We've had many people come up with different ways to create saliency maps. If you use different ways, you'll often get a completely different saliency map, which doesn't make a lot of sense. If you show the same saliency map to two different people, a lot of times they'll just project their own idea of what the agent should be doing in the game onto it. And some people have then tried to go back and do things like try to falsify these hypotheses presented in papers, doing things like turning the image around and running it back through the network, and they don't get an inverted saliency map. So I don't know if we can completely trust these, and I don't know if this is the way we should be going, which led me to try to think about, well, what other options do we have? And when I first started reading about this and coming across these problems, it occurred to me, because I have to admit, my first degree is in marketing, as shameful as that is, that I immediately thought that we need to know who the users of these are going to be. The users of these explanations should drive the explanations. And when I first think about like who the users are of reinforcement learning, I think of two very general categories. The first one would be the one that's most of the people who use reinforcement learning today. And that's going to be the researchers who either work with or create new reinforcement learning agents. As I've been talking about, ideally, we would then end up with a second group of users, which would be consumers of some kind, corporate or otherwise, who are purchasing and using and interacting with reinforcement learning based products. So what I thought is we don't expect everyone who drives a car, which is a fairly complicated thing that can honestly be dangerous, to be a really good mechanic. So how do we help them kind of understand this machine that they're operating? Well, we use dashboards. So is there something kind of equivalent for reinforcement learning that we could come up with that would let people get like a dashboard or a diagnostic printout or something of information that could help them to use these reinforcement learning agents? I got so interested in this that I made it my whole thesis project. So my thesis revolves around visualizing 4 different agents playing the game Miss Pacman in Atari. So now that you guys are through all the definitions and everything, we just get to talk about a video game. It's pretty cool. In case you're not very familiar with how this game works, Miss Pacman wanders around the maze that you see on the right-hand side here and tries to eat the little rectangles. Those are called normal pills, but they're more commonly referred to as dots. Then Miss Pacman tries to stay away from the 4 different ghosts and tries to eat the bigger rectangular things, which are called power pills. And if Miss Pacman eats a power pill, it temporarily turns the ghosts dark blue and makes them vulnerable. If Miss Pacman eats a dark blue ghost, Miss Pacman gets a large reward. But the power pills don't replenish unless Miss Pacman loses the game and has to start over or gets to the next level. Now, how does Miss Pacman lose a game? Well, Miss Pacman has 3 lives in every game, and if Miss Pacman runs into a not dark blue ghost, life is gone. Every once in a while, the fruit that you see pictured in the lower right-hand corner of the screen will pop into the maze. If Miss Pacman eats the fruit, she also gets a large reward. That's the basics of the game. I did tell you that I was going to visualize 4 different agents, and if you just put a agent into Miss Pacman and train it for 1 million time steps, and then put another one in and train it for 1 million time steps, you'll basically get the same agent. So what I had to do is during the training, I had to give the agents different reward structures. And then what I did is I would train each of the 4 agents with a different reward structure a little bit, and then I would save that model. And then I would train it a lot more and I would save that model. And then I had an evaluation process where I took all of these different models and I ran them through with the rewards set back to the normal game rewards, a 10,000 step evaluation, so that I would have kind of a common baseline to work off of. So in my visualizing of these agents, one of the interesting things that I found is that you could actually learn about the environment while you're learning about the agents. I have this really fun bit of trivia that I can tell people now, which is that the ghosts are not all the same. And you're going to see in a video on the left-hand side of the screen here, it's going to start to flash through some maps of the maze. And on each map, there are going to be some colored dots. The colored dots represent where that particular agent lost to life during its evaluation. So the dots are not going to move for a particular agent. There will be one map for each ghost, and so the color of the dot will represent how far away that ghost was when Miss Pacman lost that particular life. And what I started to notice as I was going through these visualizations is that on the whole, when my agents weren't trained very much, the red ghost ate the agents way more often than any of the other ghosts. And I got really curious what that meant. So I went and I looked it up, and now I have party trivia I can throw at people, which is that the red ghost is supposed to just chase Miss Pacman, but the other ghosts do other things. Like the orange ghost is actually trying to aim for a spot like 8 steps in front of Miss Pacman or something like that. And so not only did I learn about the environment, I learned some information about the environment specifically that could help me evaluate my, my ghosts and my results and draw some slightly different conclusions. I have information that can help me differentiate between, is this phenomena caused by the ghost behavior, which is different between ghosts, or is it caused by my agent behavior? And one example where this was actually kind of useful is I had one agent that kept getting killed by the orange and blue ghosts, which should not be particularly deadly, in the upper left-hand corner. And I went back and watched some video of this agent playing, and it turns out when this agent gets really low on pills in the maze to focus on, it gets extremely confused, and it just runs straight up that left-hand tunnel into a wall, and then just keeps going into the wall until one of those 2 ghosts comes along and eats it. It's not very good, but it's what it does. So let's go ahead and look at the different agents. What I have here is the rewards over time boring old chart that you see everywhere for all of my different agents. You can see some stuff, like you can see that some agents apparently like have a lot more games because their line stretches a lot further to the right. And some of them appear to score a lot more points because their line goes a lot higher up. But I don't know, this just doesn't tell me that much. So you can see some interesting things that you can't really explain with the chart, like what's up with these 2 short lines in the middle here. We're gonna find out. So that is the 2 lines that represent the agent that is trained to be afraid of ghosts, because every time step that the agent stays alive, it gets 1 positive point, like, yay, good job, you didn't die. And if it dies, it gets a very large negative reward that penalizes it. So I trained the agent for 2 million time steps, which is the one on the left-hand side. And then I kept training it for 18 million time steps, which is the one on the right-hand side. And what I wanted to do with each of these agents is I wanted to create a sort of, like I said, a dashboard or a summary of the agent. And so I have 4 graphs for each agent here. And starting in the upper left-hand corner, the lives left in key situations graph it's a graph of key situations which you don't really need to know about. Just know that they are chunks of time from the evaluation that are pulled aside by an algorithm to serve as a summary of the agent. So they're supposed to kind of act as a summary of the agent, but you can think of them as guided random pulls from the data. And each of these random pulls is mapped according to how many lives are left when the agent's at that point in the game. And one of the things that I did notice is that even though 5 is a really small sample size, because it's supposed to act as a summary, if you start to see a lot of key situations falling in the 1 life left category, you may not have a very good agent because it's spending too much time with only 1 life left. Pretty simple, but kind of helpful. And so you do see that on the left, there are 2 situations where the agent ends up with only 1 life left, and there are none on the right. Moving over to the upper right-hand corner, you have the actions per game chart, which is the stacked action plot. And what this shows you is the percentage of each action, the 4 actions that are available to the agent, as a percentage of the total actions taken during that game in the evaluation. What this helps with in particular is that I noticed over time that if an agent wasn't as fully trained, the stacked action plot tended to be a lot more jagged. Whereas when it was trained more, you saw more like smooth lines on the stacked action plot, which we do see between these 2 agents to some degree. One of the most interesting and helpful plots that I've actually come up with so far is the bar chart in the lower right-hand corner here. And it's kind of pink and orange. The pink is where it eats just a normal dot. The dark pink, the bigger circles, is where a power pill gets eaten. And then the gray circles are larger rewards, like eating a ghost or eating some fruit. What the height of the bar tells you is how long the game is. The number of bars tell you how many games Pacman played during the evaluation. And so looking between these 2 agents in particular, we can see that the agent on the left, which was trained less, only eats 3 power pills on average in a game. And the agent on the right, which was trained a lot more, does appear to eat all 4 power pills during a game. And then let's go and look at the last one, which is in the lower left-hand corner. And this is the one with the blue dots on it. I call it a movement map. And all that this shows us is all the places that Miss Pacman went during her 10,000 step evaluation. What you do tend to notice over time with these is that as agents are trained more, they tend to have more consistently spread out dots and less like lumps and clumpiness in this. Let's go ahead and talk about why the stacked action plots are jagged when the agent is not as well trained. I do think it might be partly associated with the environment that I chose, which is Miss Pacman. And here's why. So I have one agent on the left, which was trained for 300,000 time steps, and one agent on the right, which was trained for 23 million time steps, which is a lot more. And what I did here is the bars each represent a game, and each circle represents a step taken in the game. The size and color of the circle is the action taken at that step. And what you notice pretty quickly is that the 300,000 time step agent performs a lot of the same action in a row a lot. I think my hypothesis is that this is because the agent is still figuring out like what its limbs do. And so it's just trying something and going and going and going. And so that's what it's trained to do at this point. However, with the 23 million time step agent, in part because of the way the maze is designed, so there's not a lot of like really long straight lines in the maze. There's a short straight line and then a corner. The agent kind of has to do a lot of a consistent mix of actions to actually navigate the maze successfully. So I think that's why we see this kind of difference between these 2 like scatter plots and between the stacked action plots. The next agent I want to talk about is one that was trained only to eat power pills. It was not given rewards for anything else in the game. And it also has a bigger disparity between its training. The least trained agent on the left-hand side was trained for 700,000 time steps. And the agent that was trained more on the right-hand side was trained for full 23 million time steps. We can see again that in the key situations graph, the one on the left has more situations with only 1 life left. And we can in fact see in this case a lot more jaggedness in the stacked action plot. We can also go down to the bar chart and we can see a pretty big difference between the one that was not very well trained and the one that was very well trained. And it's kind of obvious what it is. It's not eating a lot of power pills until it's better trained. One of the interesting things about the one that's trained more, however, is that it is consistently eating all 4 power pills in a row. And so it seems that by focusing its training on power pills only, I would say that this agent has achieved its objective and it's really good at what we told it to do. So that's great. You can also look at the movement maps, and you might notice on the one that's less trained on the left-hand side that there's kind of like this clump in the lower right-hand corner. It turns out that if you go back and you watch the agent, that's the power pill that it eats first. And because it appears to have consistently learned to eat at least 1 power pill, it just kind of keeps going down to that corner. The next agent I want to talk to you guys about is the normal only agent. This agent was trained just to eat the dots and ignore everything else. So just little normal pills. And again, we kind of see the same thing with the key situations. The one that's not trained as much has more in the one life left, etc. To me, the stacked action plots don't appear any different. And so that's why it was really interesting to me to look at the bar chart here. And what you see is if you just glance between the two of them, the one on the left actually gets more big rewards, as I call them. And so my hypothesis is that this agent has, at 21 million time steps, it has overtrained to eating the power pills, or the normal pills, excuse me. And so it is actually performing far worse when it is transferred back into the environment where it now has the full reward structure of the game. And it just does not do as well. We do see when we look at the movement map in blue that even though it's not doing as well in the game, it still is covering more of the maze. So there seems to be some positive correlation almost no matter what between more training and maze coverage. I'm not going to tell you guys that rewards are completely useless, because in this case, we can actually look at the rewards and we can see that there's more to bolster our hypothesis that the agent overtrained. So the purple line is the 3 million time step agent, and the dashed brown line is the 21 million time step agent. As you can see, the one that was trained more is not getting as many rewards because it's not going up as high. Let's go and look at one last agent here. The lines that are more opaque here are all an agent that was trained with the standard rewards of the game. And we have one that was trained for 300,000 time steps, which is in pink. One that was trained for 2 million time steps, which is in the dashed gray color. One that was trained for 23 million time steps, which is in green and blue because I ran it twice. So we can see that there's a pretty big difference between 3 of the lines and 1 of the lines. That also is pretty evident in the visualizations that I've come up with. We can see that for the 300,000 time step agent, it does have a much bigger mix of lives left. And for the 23 million time step agent, it mostly hangs out in the 3 lives left, doing good, haven't lost a life yet area. The 300,000 time step agent has a more jagged stacked action plot again. And if you look at the bar charts, it's pretty obvious that one of these is doing better than the other, and it's not the one on the left-hand side. If you look at the movement map, you can also see that at 300,000 time steps, the agent's mostly exploring the bottom area of the map, whereas at 23 million, it is exploring a more consistent part of the map. But when we go to the 2 million and 23 million time step agents, they performed about the same in terms of their score. So I was curious to see if I could figure out if there was any difference between them. With the top 2, I can't really say that I do see a difference, honestly. Lives left in key situations and the stacked action plot look about the same to me. I did notice something interesting in the bar chart, however. If you look at both charts at the 400 line, which means about the 400th step in each game, with the agent on the left, which is trained for 2 million time steps, by about the 400th step, a little bit after, it's usually eating the 4th power pill. That's great, it's getting a lot of rewards. Unfortunately, if you eat all the power pills while all the ghosts are still dark blue from the previous power pills, you're like wasting the power pills. And then you have no power pills when the ghosts turn back to normal, and you're running around just trying to get away from them because you have no protection against them. So if you look at the 23 million time step agent, you can see that a little bit before the 400 or a little bit after the 400 mark, it's actually usually just getting to its 3rd power pill, which says to me that it may, in my hypothesis, be figuring out that there's some benefit to delaying eating all of the power pills at once, but it's still kind of trying to figure out how to handle that benefit and how to incorporate that benefit into its strategy, if you can call it that. You do see with the movement map in blue a little bit of a difference between the 2 maps. But to be completely honest with you guys, I found it difficult to see a difference here. And so what I did is I tried a different approach to the movement map. And what we have here is we have both the size and the color of each circle. represent the frequency of Miss Pacman visiting that spot during the evaluation. Obviously, at 300,000 time steps, it's not great. So it's a lot more green in the bottom. But then you look at the 2 million and the 23 million time step agents, and you actually can start to see a difference here. To me, a more pronounced difference in that the 23 million time step agent does appear to be traveling more consistently throughout the entire maze. I do have the yellow dot in the middle, which is because when Pacman first starts in the middle of the maze, she has to like sit there and chomp for 250 million, or not 250, wow, 250 time steps while the ghosts move around so that the ghosts get a chance to move into the maze. What I plan to do for this particular visualization is I plan to do some calculations and get those first few steps where Miss Pacman's not moving at all out so that maybe I can see something a little more different and interesting here. And so those are my visualizations with my 4 agents. And I have come to realize that part of why machine learning adopting by companies and people is not moving as fast as we maybe would like it to is in part because with deep neural networks and deep learning, people don't feel like they can trust them as much and they're not as explainable. And that's kind of worse for reinforcement learning because of the time aspect. And so I've come up with these visualizations, and my next step is going to be in the spring doing a user study to prove that hopefully people can differentiate between the agents better and can answer questions about each of the agents better with the visualizations compared to not, because I'm not just trying to create pretty pictures, I actually want to do something with these. And after that, who knows, I'll get my thesis hopefully and start work back at PNNL. Yeah, so those are my agents.
Excellent, thank you, Britt. We'll turn it to you, the audience. Do we have any questions at this time?
That was a lot of fun, hey?
I hope so.
Last chance for, it's a quiet crowd tonight, which is okay. But are there any last questions for Britt before we conclude? Okay, so be it. Thank you, Britt, for and Chris for the fantastic presentations. Britt, I believe you are officially the first grad student from WSU to present at the meetup, and there is a great silver lining to hosting these events virtually. And for all the grad students in the room today, the AI Meetup is a great place to practice your thesis presentation, or any presentation for that matter, in front of a live audience. So that is my not so subtle hint, hint, nudge, nudge. But this wraps up our first AI Meetup of the year. This meetup would not exist without the support of our community. So let's connect. If you have any questions about the meetup, or if you are interested in presenting at a future meetup, we'd love to hear from you. Again, this meetup will be available on our YouTube page very soon, but why stop there? We also encourage you to go on our YouTube page and view not only the past AI meetups, but also presentations from the AI seminars and tea time talks hosted at the University of Alberta, as well as other past lectures that we've hosted. So you don't have to wait until next month's meetup for new content. There's lots there to explore. But with that said, we do hope to see you again next month at the same time on February 18th. And once again, thank you to Chris and Britt, our 2 presenters, for sharing their time and their expertise with us. Do either of you have any final words or thank yous you'd like to send out to the internet?
Yeah, thank you to you at Amii for hosting us. And I just put in the chat the contact information if anyone wants to reach out to ISAIC. Thanks also, Brittany, for sharing the stage and helping make more sense of explainable AI as it relates to the reinforcement versus deep learning.
Awesome. And Ian, just to go back to your question, we'll be sharing the survey results. Yes, we can include the survey results within the comments of the YouTube video. So as you're watching the video, you can go into the video description and we can include some of that results there. But without further ado, we thank you all for sharing the evening with us, and we hope to see you again next time. Take care.